So today we're going to discuss section 2.5, which is on variation and applications. Now, technically speaking, the applications part of this is the word problems, but luckily the word problems in chapter 2 were significantly more straightforward than they are in chapter 1. So there's not a lot of new math in this section, but there is some new vocabulary. So we'll start with the definition of direct variation. So if a situation gives rise to a function of the form y equals kx, where k is just some positive constant number, then we say that we use one of the following several phrases. We either say that we have direct variation, that y varies directly as or sometimes with x, or that y is directly proportional to x. So in this case, k is called the variation constant and y equals k times x is called the equation of variation. So if you're ever asked for the equation of variation, that's what they want. And if you're asked for the constant of variation or the variation constant, you're just being asked for k. So let's take a look at the general strategy for how to attack these problems. So most variation problems that show up in just about any algebra book are sort of comically consistent. They always look the exact same way. The structure is pretty much identical. So the idea is as follows. So the first step involves the first sentence of a variation problem. And that sentence always tells you the type of variation that you have. So they'll either say you have direct variation or later on inverse variation or maybe joint variation. We'll talk about those later. But they always tell you exactly the type of variation that you have. So once they tell you that type of variation, write down a generic equation of variation where you don't know k. So y equals kx, for example, if you have direct variation. So the second sentence always gives you enough information in order to find the variation constant. So in the notation that we've used here, they'll give you y and x. That will allow you to solve for k. Once you've solved for k, plug that back into the generic equation of variation, and then they're going to ask you a question in the third sentence. So the third sentence will either give you y or x, and they'll ask you to solve for the other one. You plug that in using the k value that you found in step 2 here, solve for the other variable, and answer in a complete sentence. Pretty straightforward. So let's take a look at a particular example of direct variation. So the maximum number of grams of fat in a person's diet varies directly as the person's weight. A person weighing 120 pounds should have no more than 60 grams of fat per day. What's the maximum daily fat intake for a person weighing 180 pounds? So in this particular example, we're not given variables to work with. So the very first thing that we're going to do is name our variables just like we usually do in a word problem setting. So in this case, I'm going to let y be the number of grams of fat in a person's diet, and x is going to be that person's weight. Now you'll notice in the first sentence of the statement of this problem that they tell us what type of variation that we have. In fact, the exact words are the maximum number of grams of fat in a person's diet varies directly, that's the key words here, as a person's weight. So the first thing that we're going to do after we name our variables is write down our generic variation equation. In this case, y equals kx. K is just some unknown constant number, which we're going to find out in the next step. So you'll notice that in the second sentence, they tell us that a person weighing 120 pounds should have no more than 60 grams of fat in their diet per day. So what we're going to do is plug in 60 for y, which is the number of grams of fat in the person's diet, and 120 in for x, which is the person's weight. So once we plug those numbers in, what we get is 60 equals k times 120. This is a very straightforward linear equation to solve. Divide both sides by 120 and you get that k is 1/2. Now we're going to take that variation constant and plug it back into our generic variation equation. And what that's going to give us is our sort of more specific variation equation, y equals 1/2 times x. Once we have that, we look back at the third sentence, which says, what is the maximum daily fat intake for a person weighing 180 pounds? So here, 180 pounds is getting plugged in for the person's weight. So run the numbers real fast. 180 divided by 2 is 90. So we always answer in a complete sentence. And in this particular case, that's the maximum daily fat intake is 90 grams. And that would be enough to get you full points here. So now we're going to talk about inverse variation. So Basically, the idea behind direct variation is that if one quantity increases, the other quantity increases as well. And if one quantity decreases, the other quantity decreases as well. That's direct variation. With inverse variation, it's the opposite. If one quantity goes up, the other goes down, and vice versa. So sort of the classic example here is demand versus price. So let's say you're selling iPads. If you raise the price on these iPads, the demand is going to go down. And conversely, if you decrease the price on these iPads, demand is going to go up. That's inverse variation. So a little bit more specifically, if a situation gives rise to a function of the form y equals k divided by x, where again, k is just some positive constant, then we see we have inverse variation, that y varies inversely as x, or sometimes that y is inversely proportional to x. In this case, again, k is called the variation constant. The equation y equals k over x is the equation of variation. Really, the only difference here between inverse variation and direct variation is that in direct variation, you have multiplication on the right-hand side, k times x, and in inverse variation, you have division, k divided by x instead. So let's take a look at an example of inverse variation. So the weight W that a horizontal beam can support varies inversely as the length L of that beam. Suppose an 8-meter beam can support 1,200 kilograms of weight. How many kilograms can a 14-meter beam support? So you'll notice in this particular problem that they tell us which variables to use. We're supposed to use W for the weight and L for the length of the beam, both of which are capital. So in this case, we don't really need to name our variables because that step is done for us. So the first thing that we're going to do is write down our generic equation of variation. Now, in this case, in the first sentence, we're told that blah, blah, blah varies inversely, right? That's what we're looking for in that first sentence. In this case, weight varies inversely with length. So the equation that we write down for our generic equation is W equals K divided by L. That's the first sentence done. Now, the second sentence tells us that an 8-meter beam can support 1,200 kilograms. So what we're going to do is plug 1,200 in for W and 8 in for L. And once we do that, the equation that we get is 1,200 equals K divided by 8. Now we're going to multiply both sides by 8 to solve for K. And what we get is that K equals 9,600. You'll notice that I'm not using units along the way here. I'm going to save those until the very end and I'll throw my units on. So I take that K value and I plug it back into the generic equation of variation. And what that tells me is that W equals 9,600 divided by L. Finally, the third sentence in the question says how many kilograms can a 14-meter beam support? In other words, what weight can a 14-meter beam support? So we're going to take that 14 and plug it in for L. We divide 9,600 by 14, and what we get is roughly 685.71. That's rounded to 2 decimal places. Some problems will ask for that, in which case you can round and use decimal places. That's just fun. So finally, we answer our question in the complete sentence. A 14-meter beam can support around 685.71 kilograms of weight. So the last type of variation that we're going to talk about today is joint variation. So essentially the idea behind joint variation is it's direct variation, but you have more than one independent variable. A little more specifically, we say that y varies jointly as x and z if there exists a positive constant k such that y equals k times x times z. So let's take a look at an example using joint variation. So suppose that y varies jointly as x and z and that y equals 56 when x equals 7 and z equals 8. We want to find the equation of variation. So essentially the strategy here is the same as the strategy that we had in direct and inverse variation. The only difference is we get to skip step 3 here. There's not really a step 3, so it's a little more straightforward than the other examples that we've done in this section. So the first thing that we're going to do is the same as what we did in the other 2 examples, which is to write down the generic equation of variation here. In this case, y equals k times x times z because we have joint variation. Next up, we're going to plug in 56 for y, 7 for x, and 8 for z. And what we'll find is that 56 equals k times 56 because 56 is 8 times 7. Divide both sides by 56 to solve for k, and what we get is k equals 1. So we take that k equals 1, we plug it back into the equation of variation, the generic equation of variation, and what we get is y equals x times z. And that's about it. Thus concludes our notes on section 2.5. I'll see you guys next class.